So exceptionally, it's being held in the lab auditorium because yesterday was a well-deserved day of holiday, n'est-ce pas? I would like to start by asking for a few seconds of silence for the Ukrainians. Fortunately, I don't have the Ukrainian flag today, so you can imagine the flag. I think you know what it looks like by now. Today I want to talk about formal models, how to model distributed systems, and next week then I'll talk about how to write algorithms. That's next week. The week after that I want to talk about a major, very important thing that was discovered or invented in the 1990s, failure detectors. So with these three things, we will really be able to start making systems. So today I want to talk about formal models. The first, let me give you kind of general scientific introduction. What is a model? Well, we want to make some kind of a mathematical abstraction of our system. That's very general. Everybody who does science does that. It's very general. In my view, so the real world is very complicated. My personal opinion is that it's infinitely complicated, and that's hard to model. Infinity is very hard. So we will simplify reality, make a finite approximation. And this is very general. In all your courses where you learn science, the whole point is defining the right model. So Isaac Newton was very lucky in the 17th century that his inverse square model really describes well the solar system. Because if we were be living inside of a cluster nebula, that would not be possible. You know, there's a famous science fiction story by Isaac Asimov called Nightfall, about a world which lives with 6 suns that are moving around all over the place. Those guys had a hard time figuring out the right model. It took them very long to figure out that inverse square was the right model. So defining the right model is very important. Somehow nature is helping us for that. That's very strange. Why does nature help us? But that's not what we will discuss in this course. That's more philosophy. In this course we will use models. We will define algorithms, solve problems. We will also understand, analyze. So modeling is super important, okay? And in all courses where you really want to understand things, you do modeling. And in engineering, there are 2 important kinds of models. There are the discrete and the continuous ones. The discrete ones, where the system obeys a discrete law. Transition systems, for example, discrete time steps, it switches from one state to the next. In a continuous model, usually you have differential equations, which I'm sure you understand very well. But in this course, I will not talk about differential equations. In fact, you will learn a whole different way of modeling, a way that is maybe not enough emphasized, a discrete. So a distributed computing system, we will assume it's a discrete system, okay? And the biggest challenge for models is finding the right level of abstraction. So I'm going to give you a model, and it took many years of hard thinking for researchers, scientists, and engineers to figure it out. Hopefully, you will see that it's a nice model. So this model has to have some power. And what kind of power does the model have to have? The most important, or one of the most important, is impossibility proofs. It has to be strong enough that you can say some things are impossible. Like I said last week, on an asynchronous system where at least one failure can happen, it is impossible to construct consensus, a statement about all possible algorithms. Okay, so we want that. But the model should not be too complicated. So there's actually 3 properties we want. And in this course, I try to make a balance and give you a really nice model. The first property is complete. It explains everything we want. Nothing is missing. It is correct. It reflects the real world system. It doesn't do weird stuff that you don't see in the real world. No mistakes. And finally, it's concise. It's not too complicated. Okay? So we're going to look at that. So that's kind of general introduction. Now I want to show you a model of distributed systems. And it's a little bit subtle. The main thing is you have single nodes and you have the network. How do you model the network in a nice way? Now you can make network protocols like TCP, but that's actually very complicated and I don't want to base it on any kind of existing protocol. So the real hard point is the model of the network. So we're going to see that here. So what is a distributed system? It's a set of nodes, here, P1, P2, P3, P4, that send messages, and they're running a common algorithm, okay? So nodes talking to each other, and they're working together, and they present themselves like a single system, okay? So how do we model that? We're going to see it in 2 parts, okay? How do you model a single node? First, we're going to look at single nodes, and the second part will be the network. So the real subtlety in this whole business will be the network. So here I'm going to make kind of a summary. So one node. First we look at one node, and then we look at what happens when you have many nodes. Okay? So the node has a state, and there's different kinds of states. We're going to see the local state, but also the network has state on the node, so we will have a network state here. Because the network state is stored on the node, okay? It's not stored in the network, it's stored on the node. Okay, so let me talk first about a single node, and then we'll talk about many nodes. Okay, one node. So it seems to be quite simple. It's not really so complicated, but you have to be careful. So a single node has its own local state, variables, and it has neighboring nodes. So we'll assume that the whole network is kind of a graph where each node has a set of neighbors. And the node can do 2 things. It can communicate, send and receive messages to neighbors, and it can do local computation. Okay, so that seems quite simple. And the node's behavior locally, we will model it by what's called a state transition system. So this is like a finite state machine. So basically, at any instant, the node is in a state, and it can make transitions to another state. But maybe it's not finite. Also, there's no real input, because information is coming from the network to start this thing. And so this whole state transition system is communicating with the network. Okay? Okay. So a state transition system is a fairly straightforward, not complicated thing. You have states, just like the values of the variables. You have rules for which state to go from each state. So this is like the program that's running. And then you have some initial states. So this rule is also called a transition function. Okay, so that's kind of straightforward, That's not too hard. So here's a simple example. Here I have a little program in some weird Pascal-like language. X is 0, then while x less than 2, x gets x plus 1, and x gets 1. And using a graph, you can see that there's states. So x has the value 0, state x0, x1, x2, x1 prime. So you have this transition function from x0 go to x1, from x1 to x2. So this is a very simple thing. I'm not going to spend so much time on this. The real issue is the connections, okay, of the nodes. That's where it gets a little bit subtle. Okay, so now let's model one node. And now I want to talk about the network. How do we model the network? And I will give you one specific way of modeling the network, which works well. There are other ways. There may be other ways you can imagine. But in this course, we'll look at this one way. The node here, P2, it has two kinds of state. A local state and a network state. So the network is modeled on the node, okay? It's modeled at the node. There's no state that's inside the network in this model. The state is always on the node, okay? So there's nothing, the network is like an empty thing. There's nothing inside there. There's no state. You could imagine a different kind of model where you put something in the network and it's floating inside and it comes out. But actually that's not so nice, because that makes things more complicated for various reasons. It's easy to have all the state at the node. So the node is going to model the network, okay? So there's going to be like a piece of the network at the node. And this is called the in buff and the out buff. The incoming messages and the outcoming messages. This node P2 has neighbors, and each neighbor will have an in buff set and an out buff set. So these in buff and out buff is like an array or vector of sets of messages. Okay? So a message coming in from another node, let's say we have P1 going to P2. Here you have the state, you have in buff, out buff. And let's say this is in buff 1 because it's going to node 1. Here we have another state. And let's go from S2, S1, in buff 2, out buff 2. So P1 is connected to P2, so you have in buff 2, out buff 2. So these are sets. P2 is connected to P1, so you have in buff 1, out buff 1. So how does the network work? So when P2 sends a message to P1, it puts the message inside the in buff. Inside the out buff. I'm sorry, it's going out. Okay? When P2 sends a message to N1, it puts a message in the out buff. And that means the message is kind of in the network. In the model, it's in the out buff. But you can think of the message as being in the network. So once you put it in the out buff, it's gone. And then somehow the message will travel from P2 to P1. And how does that work? Well, there's an instantaneous transition. So at some point, the message will disappear here. This becomes empty again. And will appear in the in buff here. This is a transition. Instantaneous. So in the model, it's like once you put the message in the out buff, some later time it will puff, disappear here, and appear here. Ping, magically, it's transported from P2 to P1. Of course, the real network is not going to work like that, because it takes time. But these two transitions, so putting M in the out buff and doing the transition, are two separate things. So there's going to be some different instant. So the time of the travel is modeled by that. Okay? So this is a very simple network model. Okay? Much simpler than TCP or something like that, or IP. There's no packets. There's no sequencing or anything, sequence number, anything like that. It's just, you put a message in the out buff, and later, some later time, the message magically appears in the in buff of the other guy. And that's it. And we will model failure like this. So a failure, for example, happens when the message disappears from the out buff and appears nowhere. Okay, so that would be a failure. Okay. So this is how we model the network. It's only state at the node. Okay, it's the state of one node. And here's an example. So this is one node. This is P2. P2 has 3 neighbors, 1, 2, and 3. And there's 3 out buffs here and in buffs. So it starts out empty. So X is the local variable, 0. All these are empty. We do a transition here, arrow. In buff 1 is now M0. A message has arrived from 1 and appears in there. And now the message can be read. There's another transition where we do a local computation. So the message disappears from the in buff. The local state changes and a message is sent. A reply goes into the out buff of 1. Okay? Doesn't have to. It may not, but in this case, there's also a message sent. So this transition will clear out the in buffs. It will do local computation, and it might send a message on the out buff. Okay? Fine. Now another transition. So we follow the arrow, actually comes to here. Okay? Now another message appears on in buff 2. This is not changing now. So this message M1 is in the network. It's gone. But so far nothing is happening to it. It's just in the network. But another message appears on in buff 2. And then another transition. Another message, M3. So 2 messages arrive on in buff 2, M2 and M3. And now again we will do a computation. We will read the messages. So we zero the in buffs. Goes to empty. We will update the local state. We do some computation. And we send a message again. So here another message is sent. So you see, there's a couple of different possibilities. There's messages that can appear in the in buffs. And then there's local computation, which reads the in buffs and maybe sets the out buffs. So those are the 2 kinds of transition, okay? So you see how we model the network, okay? It looks like there's a lot of stuff here, but in fact it's very easy, huh? You put a message in the out buff, and it's gone. Some later time, poof, it magically appears in the in buff on the other side. Here we only see one side, huh? We see a message appearing in buff 1, but before that it has been on the out buff of node 1, sending to P2. Okay? So the transition brings it here. See how that works? So that's how we model the network. Yeah?
Just a question. For the X, it represents the current state of the node?
The local variables in the program. So here I have 1. It's like, it could be database, so maybe a lot of data. It's the local stuff, everything that's not the network. Okay? So here it's only 1 little variable, but it could be a lot of variables. But the out in buff is just the network state. Okay? See how it works? Question?
Who does the cleaning of the out buff? I mean, like...
Yes. Well, this out buff here, eventually there's a magic transition where this one disappears and it appears on the in buff of the node on the other side.
Okay.
Okay, so here we have something in the out buff. This is the M1, and I didn't show it here, but you will see it in a minute. There's a transition, which is called the delivery, which magically transports instantaneously the message from P2 to P1. And it appears on the in buff of P1, and it disappears in the out buff of P2. Okay, so this is the model. Of course, it's not going to be instantaneous in real life, but making it instantaneous in the model actually seems to be a good way of modeling. If you want to model this with TCP, it'll be different. Yeah, question?
But if it fails to deliver, when do we know that we should be able to?
If it fails to deliver, well, it depends on what kind of failure. What is the failure model you're thinking of?
I don't know, the recipient doesn't have a connection.
So there's a network interruption.
Yes.
Well, then it depends on the protocol. So, for example, the message might be lost. So we can model failure by saying that M1 disappears, but it does not appear anywhere else. So we add a transition where the M1 just disappears. Okay, but we will see the failures in another lecture where there's a failure detector telling us when something happens. So usually the way we model failures is the node fails. And when the node fails, all the network state on the node disappears. Okay? This is a crash stop failure. So if this node fails, we assume somehow that M1 is somehow still close to this node, and if the node fails, it's still like in the networking software of this node. So if this node fails, the M1 will disappear. But eventually there's a transition and M1 is magically transported to the other side. If the node fails after that transition, then the message is still there, of course. Because the message has somehow already got close enough to the other one. So either the message disappears in the source or it disappears at the destination. Okay? This is actually similar in real life. If you make TCP connections between two nodes, you send a message, and if one of those two nodes fails, depending on how far the message got, it can disappear if the source node fails, or it can be not disappear, arriving, even if the source node fails. If it already got into the buffer at the other side, for example, then the source node failure will have no effect. So this model can respect that behavior. Okay? But failure is a thing. Okay? So all state, except the outbuffs, is what's called accessible state. So the inbuffs is reading, so this is accessible. That means it's actually kind of local. Whereas the outbuff, it's not accessible. It's like in the network. So for the model, the outbuff is not readable. It's only writable. It's write only. Okay, the outbuff you can only write. The inbuff you can read it, and the outbuff you can write it. So you're not allowed to read an outbuff, in fact. So once you've written the outbuff, it's in the network with the model. Okay? And so we have actually a function f that we can define that takes all of this as input. It's mostly the accessible state. And in the output, it will read all the inbuffs, it will read the local variables, and it will send messages. It will add at most one message to each outbuff. So that's how we're going to define. If you want to send two messages, then you need to make two transitions. Okay? But we're only allowing a message on each outbuff. In one transition, one message on each outbuff. Okay? And now I'm going to show you the most complicated slide of today, but it's actually intuitive, which I'll explain. So the state of a node is a triple, I, O, and S. So S is the local state, I is a vector of inbuffs, and O is a vector of outbuffs, and the network state is a pair I-O. Okay? Fine. And little s can be very big, can be lots of variables. And I and O are vectors, because each channel has one buffer. Okay, one inbuff and one outbuff. Now we have a correctness condition for this transition function. The transition function takes the state and goes to another state. And this completely defines the correctness. And it's actually very intuitive. Assume that we have I1, O1, S1. This gives I2, O2, S2. Assume we have another state, I3, O3, S3, giving I4, O4, S4. So what are the correctness conditions? There's actually 4 conditions. First condition, all in buffs are empty after. So I2 and I4 must be empty, okay? Which means we have read all the incoming messages. So that's the first condition. The second condition, if I1 and I3 are equal, and S1 and S3 are equal, then S2 is equal to S4, which means the computation is deterministic. The inputs are the same, and the outputs, S2 and S4, have to be the same, except that we don't read the outbuffs. Okay? We don't care about the O's because they're write only. But the incoming messages and the state completely determine the computation. So it's deterministic. That's this condition here. And now there's a condition, 2 conditions on the network. Okay? So we know that O1 has to be a subset for every I of O2. That means the F can only add messages to the outbuffs, it cannot remove them. Okay? The O2 has to be at least as big, not smaller, than O1, which means that we can only send messages in the outbuffs. We're not allowed to remove. Okay? That's this condition here. And the final condition is that O2 minus O1 is the same as O4 minus O3. That means if there was already some messages in the O's, and we do F, we will add more messages. Okay, we can add more messages, which is O2 minus O1, but it has to be the same here. So the outpuffs will keep their old messages. When we send a message, we can add more messages, but they have to keep their old messages. So this complexity is basically needed just to explain how the network works. Okay? So this is the whole model, and it follows completely the intuition that I gave you. When you put in the outpuff, the message is gone. It's in the network. And when it's in the in-buff, you can read it. Yeah?
I just have a question. You said that each state is for each neighbor node, or is it just for the node? That's far I got.
The S, what do you mean? The S state is, so each node has local memory, and that is local variables, and that's S.
So it's it's independent from the neighbors.
Yes.
Okay.
And then each node has a network where it connects to a set of neighbors. So here we have K neighbors. So it's a graph. K neighbors, and for each neighbor, it has an in-buff and an out-buff. I1, O1, I2, O2. And these are sets of messages. Okay? That's it. So each neighbor, you basically send separately. So it's like communication channels, huh? You should send separately. If the machine is connected to 2 routers, then this would correspond to two channels here, and you would have 2 in-buffs and 2 outbuffs. Okay, and that's it. That's the model. The network state is local at the node. The outbuffs are write only, and the in-buffs are read. They're read only. Okay? See how that works? So that's the intuition. It's important to understand the intuition. Okay? So how does the execution work? Okay, now let's talk a little. Now let's discuss a little bit. So how does a node run? So in fact, it's in real life. How does it work? Well, basically, it waits for a message. When a message appears in the in-buff, it does some local computation, and it might send some messages. Okay, so that's how it works. When the message appears on the in-buff, then it's able to do a transition, so it can do a local computation, which makes this message disappear. The state here will change, and it might the message appears on the in-buff, the state will change, and it might send on the out-buff. Okay, so that's how it works. And it just loops. So the single node in this model is like a sequential machine. Okay, it's looping like this. Okay. So this looks pretty deterministic, okay? So what do you think now? Now I've given you basically the model, huh? We'll talk about many nodes later, but this model of one node, it basically tells you the whole thing, okay? So what do you think? Is it interesting? Is it correct? You see mistakes here? Is it deterministic? Well, real distributed systems are not deterministic, but this looks pretty deterministic, no? Where's the non-determinism? What about atomicity? Is the execution of one node atomic? What do you think? Now, I want you to think a little. What is this reasonable? Is this correct? You see problems here? Where is the non-determinism, for example? What do you think of this model? That's a skill that takes some learning. When someone gives you a model, you have to think with that model. Okay? So what is this model? First of all, what do you think? You think it's correct? Is it reasonable? Do you see anything wrong with it or not? Maybe it's correct. I'm not. When I say that, I'm not trying to trick you up. So, what do you think of this model? Yeah.
The non-determinism is where we receive the message?
Yeah, the non-determinism, exactly. It comes from the messages. It's not the local machine. Because when you send a message in put it in the out buff, it appears on the in buff some later transition, but we don't know how far along. So the non-determinism comes purely from the messages here, okay? The local computation is completely deterministic. Is that reasonable? So that's how the model is, huh? The non-determinism is clearly here in the messages. It's not in the local computation. Is that okay? What do you think? That's how this model has decided to understand the world. Is that reasonable? What do you think? Is it reasonable to do that? To put all the non-determinism in the... Basically, it's all in the network, the non-determinism. The local nodes are doing purely deterministic computation. A local node, this local computation, as we have seen, is purely deterministic. And this is a sequential loop. So there's no non-determinism here. The only non-determinism is what is the time when you receive the message travel time, which can vary. So that's how this model decides to understand the world. Is that reasonable? Yeah?
I just have a remark. Maybe it just waits forever if there is no neighbors, or if there is no...
If there is no messages, so that's one property. If there are no messages, this one will wait forever, indeed. So that's what this model... Is that reasonable? Does the real world work like that?
No.
Why not?
Well, if there is no messages, then it means it must be a problem.
Oh yeah, but maybe you have a distributed system that has a failure. And would this model correctly model that? I mean, let's say that node 2 needs to receive a message from node 1. Node 1 fails, node 2 will never receive that message. So in this model, node 2 will wait forever. So that's kind of an error, right? Wrong behavior. So that's how this model would understand that kind of failure.
Well, it will not really understand because it doesn't know if it just waits forever or if there is a failure.
Yeah. So in the underlying system, this is what really happens, huh? But we will add something else. We will add timers to this model and failure detectors. Okay? So this model is actually reasonable, but maybe it's not the simplest for making fault-tolerant algorithms. But in terms of modeling the real world, this is actually correct. You can model the real world like this, and it's reasonable. What about atomicity? Do you know an atomic execution? It is an execution where there is no intermediate state. You see the beginning and the ending state, and it's as if the transition was instantaneous. So the intermediate states are not detectable. Is this atomic? Does this have that behavior? What do you think? It doesn't have to be really instantaneous, huh? It has to be, the semantics has to be as if it was instantaneous. Which means that in the model, you can never see intermediate states. You only see beginning state of a transition and ending state. Is this satisfied by this model? What do you think? Yeah?
Reading from the inbuff, doing computation and sending is 3 steps. It's not one coming.
But where do you read for the inbuff here?
When you receive the message.
This one. And then we do a computation in step 2. And when the computation is finished, you again read the message. So where do you see the intermediate state? Here.
Between doing the local computation and sending.
But it's all done here. The local computation and the sends are done in step 2. And in step 2, you don't read. So a transition, okay, maybe I'm not clear enough. A transition function starts from a state and goes to another state. So it defines the state. And in the model, this is an instantaneous state. But here, the messages will never see intermediate states. The messages, the time when the message is taken is in point 1 here. So it's always here. It's not in between the local computation. So you will never, the messages will never see intermediate states in this model. Huh? Right? You can disagree with me, but you have to explain why. That's the only condition. Sometimes I say wrong things, but if I say something wrong, you have to tell me why I'm wrong. Okay? So I would say this is atomic because the messages are taken at a particular, well-defined time instant here. And at this time instant, the state is in a consistent condition. So we have completely executed the local computation, so we are in a valid state. So when we start the second local computation, we have a message and a valid local state. And then we go to a new valid local state. Okay? So in that sense, this is an atomic execution. Okay? Right? Yeah, it is. Huh? Yeah?
If the node crashes.
Okay, failure. So you're not talking about atomic, but a failure if a node crashes.
Yes, but
Yeah?
if we consider an execution mistake an atomic time, it means that when a node needs time to make execution.
Okay, so you're saying, what if the node crashes during number 2? Is that what you're saying? This might take some time, huh? This might take a lot of time. Maybe it's doing big computation here, and it can crash during that time, right? Is that what you're saying?
No, I say we are considering the execution time to be atomic.
The execution is atomic. It does not mean that the computation is instantaneous, huh?
Okay.
Atomicity is a semantic property. So it's as if, so the behavior of the system is as if it were instantaneous. That means we see in the same states. But it doesn't have to be actually instantaneous. Huh? It's in fact not possible for it to be actually instantaneous. But it is possible for it to be as if it were instantaneous, like a transaction. Huh? If you perform a transaction, so here we're not doing transaction, but a transaction is a typical example of an atomic operation, and the system is designed so that when you do a transaction, you either see the final state or you see the initial state if the transaction is aborted. But you will never see an intermediate state. So a program doing transactions will never see intermediate states. Okay, so that's how the transaction is implemented. Even though it takes time, you never see those intermediate states. So it's atomic. So here we have a similar thing, because the messages are only read when the system is in a consistent state here. It's never in between. So we allow the local computation to finish completely. and then we wait for the next message. So we're always getting the message when the system is in a consistent state, according to the transition function. Yeah?
Can the local computation, does local computation include possibility of clearing the input?
Well, it does, according to the model. So what this number 2 does is it will clear the in buffs, it will update the local state, and it might put things in the out buffs. That's what the local computation does, according to the model.
Then we might have a case with non-determinism. If we receive one message, and this message, while we put this message, we have received 2 new messages.
No, the message only comes in the in buff at point 1. It will never come into the in buff here. This is the only point where the message is allowed to join the in buff. But it is possible for a message to come in the in buff, and later on, another message comes in the in buff. 2 receives. And there's a local computation in between. So you can have M1 in the in buff, and do local computation, M2 and local computation. But another situation is you receive both M1 and M2, and then you do the local computation. So that's different. So that is non-deterministic. But that's a non-determinism in the network. Because it depends on the timing. You see the 2 cases I'm looking at? So if we have, so the in buff, we get M1. We have a state, S1, and then we do it's empty, we go to state S2, and now we get a new message in the in buff, and we do another computation. So here we have a computation, and here we have another one. But we could have this, M1, S1, we have M1 and 2, S1, and then we do a computation. And then we will have another state, S4, and S3 and S4 were not the same. So this is non-deterministic, huh? These 2 messages arriving, but one of them is a little bit slower here, so we're able to do local computation before M2 arrives. Huh? Whereas in this case, both messages arrive very fast, and then we do the local computation here. Right? See that? So this is an example of non-determinism, but it's not because of the node, it's because of the network. Right? It's because of the timing when these messages appear. So that's a network behavior. Okay? Okay, is that clear? It's not so complicated, but it's important to understand. So now we look at many nodes. So this is all one node. Huh? We're focusing on one node here. But now we look at many nodes. And a distributed system is usually many nodes. We have a full system. So here is an example of a system with 3 nodes, P1, P2, P3, and each node has its own state with the X's and the outs and the in buffs. Huh? Okay? And we call this, so we have to make a word here. I say this is the state of a node. But I'm not going to talk about the state of a distributed system because that's confusing. If I say state, what am I talking about? One node or many nodes? So in the distributed system community, people use a different word for the state of the whole system. Okay? But it is just the state of the whole system. Okay? It's the configuration. So the configuration is basically all the states of all the nodes taken together. So C is a configuration, and each of these Q's is a state of a node. So it's basically the state of the system, huh? But it's not called state, it's called configuration. See that? So in this course, and in the distributed system community, it's always, whenever I want to talk about the state of a whole distributed system, I'm going to say configuration. But otherwise it's the same thing. Huh? And the way I remember is that configuration is a big word and state is a small word. Distributed system is big. Okay. Okay, good. Okay, we have an initial configuration when each of the nodes is in the initial state. Okay. Now we want to look at the whole system. The whole system is executing. So each of these nodes can do transitions, huh? But the whole system is doing different things. It can either do a computation, this is local computation, or it can send a message. So for the whole system, there's two kinds of things that can happen. Either each node is doing a computation. Basically, this is reading the inbuffs, doing the local computation, or it's doing delivery event. Delivery event is actually the magic transition of M to here, from here to here. Right? This is called the delivery event. So for the whole system, we have two kinds of things. And these are called events. We have a local thing that's just in one node, called computation event. And we have a thing between two nodes. This is the magic transportation of the message from node I to J. And this is called a delivery event. Okay? So basically it's like this. And this is what it means. So a computation event, comp I, is node I, we apply the transition function. That's it. And the delivery event, del ijm, is we instantaneously transfer the message M from the outbuff of pi to the inbuff of pj. And those are the only two things that can happen. Okay? So the full system is actually only doing two kinds of things. A local computation and delivery. And that's it. Okay, so it's actually kind of simple, huh? And it's completely modeled. So the whole system is executing, and it starts in configuration C0, and it does an event, which is either comp or del, goes into C1, it does another event, goes into C2, and so on. So that's the execution of the whole system. Another way of writing that, which I will often do, is the following. It's just a different notation. You start with C0, you have E1, go into C1, start E2. So maybe this is more intuitive for some people. So the C is the configuration, and you have a transition from C0 to C1, which is defined by this event. And the event can be either a comp, I, or del, and that's it, huh? With the message. And this goes on forever. It's infinite. That is the execution. That's it. That is the formal definition of an execution of a distributed system. Okay? And the E's, the EK, can either be comp event. So this is applying PI's transition function on I state into configuration CK minus 1. Okay? And the E can be a del event. This is the configuration changes from CK minus 1 to CK by moving M from I's outbuff for the link IJ to J's inbuff. So this is a single transition. Huh? So there's two kinds of things. There's local computation, and then there's these network events. Okay? And that's it. That's how the distributed system runs. Okay? So what do you think? And the rest of the course today, I will explain more about this so that you understand it better, but that's it, basically. It's reasonable? You see how it's running? Nothing unusual going on. So here's an example. So here we have a system with 3 nodes. P1 has 1 neighbor, P3 has 1 neighbor, and P2 has 2 neighbors. Here we have a configuration. with the 3 states here, but this is the configuration. We have an event, del to 3 M7. That means from 2 to 3, the message M7 will be transferred from the out buff of P2 to the in buff of P3. The 2 red ones here. You see? That's the transition here. Boom. And here we have a comp3 event. So here we have M7 in the in buff. So it disappears. Empty. The local state is changed. It's 12. And it actually sends a message. There's an M8 in the out buff. So that's an example of a comp event. And the whole system is doing like that. So the only way that states can change is single nodes change or pairs of nodes change. You never have transition where 3 nodes are changing together. Okay? It's single nodes or pairs. So the single node is a local computation, and the pair is when you have a message going from one to the other. Okay? So that's the model. Okay? So that's it. Basically, there's some terminology inside execution. If you focus on a single process, then you have a transition for that process, and you can say a transition is applicable if it actually is part of an execution. Okay? A del ijm is applicable if there really is an m in the out buff. If there's no m in the out buff, then this thing doesn't mean anything. Okay? There has to be m, which is some particular message, in the out buff of I for this del to be something that you can do. Otherwise, you can't do it. Okay? And so you can look at single nodes. So here's the whole system. This is a simple one with 2 nodes. It's doing a comp here. But here we're only looking at node 2. So it's like we put on glasses and we only look at what's happening on node 2. And on node 2 we just have its own little transition here. So you can always go from one node to a distributed system or back. Okay? Okay. Okay, that's the model. What do you think of that? That's it? I think I'd make a break. No. That's it. That's the model. But after the break, we look at, try to understand executions. We will especially look at causality. Okay? We'll start looking at how these things are connected to each other. Because in real system, you have lots of things happening, and some things depend on other things, so that's causality. But that's part of this. Okay? It's part of execution. Okay? So we make the break now. So now I want to know what's an execution of. It's you have a bunch of nodes. Each node does local computation, and you can also send messages. We kind of formalized that. The nodes are deterministic. They do like this. They get the message, they update the state, they send messages, and they keep doing like that. Okay? The non-determinism comes from the network, from the asynchrony. That means when you have a del, a delivery, so the del is what makes the message appear. You don't know when it's done. It could be done now, or it could be done later. So the del that you can do here, maybe it's here, okay? The del can be delayed, because once the message is in the out buff, the only way to transfer is to do a del. So once it's in the out buff, the deliver can be delayed. So this is how we model it. So this is actually asynchronous, okay? And we call a schedule. The schedule is an important thing. The schedule is just the E's. The schedule is just the events. We don't care about the configuration. we're looking at the events. So this is called the schedule. This determines the execution factor. Each of these events is either a delivery event or computation. The asynchrony, so the delay, you know asynchronous can be arbitrary, is determined by when you do the del. Okay? The processing is determined by the comp. But the dels can be delayed. And so you can have, if I have two dels, both going to P3, one of them can be delayed. So the order can change if one of them is delayed. Huh? So you introduce non-determinism. Okay? All non-determinism comes from the order inside this schedule. Okay? And the schedule determines everything. Okay? If you're given the initial configuration, the schedule tells you everything. With the schedule, you could go compute everything. Okay? So all the information is in there. But you can't always the schedules. The del, you can only do it if there's an M in the out buff, okay, in the previous configuration. So you cannot make the del go earlier. You can delay a del, make it go later, but you can't really make it go earlier, okay? Okay, now let's see what kind of, how should the executions work? We have this thing, it's called admissible execution. But do you remember when you do concurrent programming with threads? Remember the threads have to be fair. Huh? You remember that? When I have n threads running, that means the scheduler, which is running on a single processor, it has to not let a thread be starving. That means every thread must be chosen in finite time. So this is called fairness. Do you remember that? Remember fairness? You should. But in a distributed system, we have also that. But we have a little bit more. Because a distributed system is like a concurrent system plus the network. Okay? And this is called admissible. So an execution in a distributed system should be admissible. If it's not admissible, then there's something wrong. And there's two conditions. And one of them is that every process has an infinite number of comp I. That means that a process is not starving. The process corresponds to the thread here. This is exactly thread fairness in a concurrent system. So admissible execution is just generalizing fairness from concurrency. Because we have a little bit more. We have a network now. And the network takes time, and messages go on the network. When I send the message, it eventually has to be delivered. If I put a message in an out buff, there must be a del taking it, putting it back in the in buff. Okay? It must be delivered. Otherwise, the message will stay in the network forever. It's like a memory leak. The message is kind of floating in the network and never received. So this is not good. So we assume that every message sent is eventually delivered after finite time. This is a fairness condition for the network. Okay? See, we have two fairness conditions here. So admissible execution is just a very natural extension of fairness for a distributed system. Notice executions are infinitely long. Why are they infinitely long? Why not finite length or something? Well, it has to be infinite, actually, because a message can wait an arbitrarily long finite time before being delivered. That's the asynchronous model. Remember what we saw last week? In the asynchronous model, when you send a message, it can take arbitrary time, and it can be even very, very long. And in this model, this means that executions are infinite. The del event must appear in a finite time, but it can be very, very far, and we don't want to put a limit on that. It's unbounded, okay? Of course, when you actually run an algorithm, eventually the algorithm will terminate, and you're done, and that's finite time, But after that, so technically the execution still continues, even though it's not doing anything anymore. So they're like dummy transitions. But it has to be infinitely long. The formal structure has to be infinite because messages take arbitrarily long time. Okay? So this is the model of asynchronous system. Okay? This model is modeling an asynchronous system. We can also model a synchronous system. Remember, we have the two streams, huh? Asynchronous on one side, synchronous when there's an upper bound. We can also, with a small change, we can model synchronous system. Basically, we partition. We have like global time, and it's called rounds. It's like boxing match, huh? You have first round, second round, third round. In each round, every process can send one message to every neighbor. All messages are delivered, and every process allowed to do computation. And in every round, it's like that. That means the round kind of models the upper bound on the computation. When the round is finished and when we start the next round, if you didn't receive a message from a process, that means the process has failed. Okay? So a synchronous system is modeled by global kind of lockstep execution. So the round corresponds to the upper bound in the real world. So this model has no time numbers attached to these events. It's all abstract, but the round will correspond to the upper bound. A process allowed to send a message to every neighbor inside the round. And it has to arrive, deliver, inside the round, which means less than the upper bound. Okay? So the way to model a synchronous system is you have these lockstep execution where all processes do this in every round. Okay? It's like that. So you can make a precise definition. So there's a delivery event for every message in all outputs. There's one computation event on every process. Okay? Notice that in a synchronous system, all executions are admissible because you're doing comp events on every process in every round, and all messages are delivered in every round. So there's no problem. So in fact, every execution is admissible. And they're still infinite. Okay? So that's how you would do this synchronous. So notice I still have not defined partially synchronous. You see, I defined synchronous and asynchronous here in this model. Partially synchronous, we will define it here, okay? And it's very important, it's related to the failure detector. Partial synchrony, you will see it here. So far we define asynchronous and synchronous. Okay, so that's nice, and you know admissible executions. So we know how to do executions. But now I want to talk about causality. Causality, of course, this is a very ancient concept. Aristotle has this very nice work on causality, but I'm not going to talk about Aristotle. I'm only going to talk about what he calls effective cause, when there's an actual thing before another thing that can be considered the thing that makes that other thing possible. Okay? In order to do that, I'm going to now ask you some questions. Consider these two executions. I start from C0. At C0, I do comp 1, which goes to C1. Then I do comp 2, which goes to C2. Okay? But now I do another execution. I start from C0. I first do comp 2, which goes to C1 prime, some different thing. Then I do comp 1, but it goes to the same C2. If I switch these two comps, I'm at the same configuration. Why? What do you think? Why is that? This is true. I'm telling you, if you do this, you will always end up at the same configuration. Why is that? This is something, if you intuitively see what is computation event, this is a very simple thing. But why is it? Two different comp events can be switched. Why? What do you think? An idea? What does it mean? You have to understand what it means. And then you see, of course, it's obvious, yeah?
Is it because you compute different in buffers? So if we compute the first one and the second one in different orders, it doesn't matter?
Well, yeah, you're on two different processes. This one is looking at the in-buff of number 1 and the state of number 1. This one is looking at the in-buff of number 2. And no messages are being sent between the two.
They're independent, sort of to speak.
Yeah, they're independent. Can you say a little bit more? That's all correct, what you say. But you can say it in a more stronger way, maybe.
And they're deterministic in that sense?
Yeah, there is, of course, they're deterministic. Yeah, that's completely correct. But why, can they be switched? What's really going on here?
Well, they're not related to each other. So
They're not related. Well, I have two processors, number 1 and number 2. They're sitting next to each other, and they're not sending messages. Yeah, clearly. Yeah.
Yeah, commutative operations. Like
This is commutative, but why is it commutative?
It could be an operation like addition.
Any comp event is commutative with any other comp event here. It could be an addition, but it could be very complicated database here. Fine. Any two comp events on different processes are commutative. Why is that? It's actually very intuitive. It's a very simple thing, what is going on here. See that? I have two processors running. One is doing computation, and the other one is also doing computation, and they're not talking to each other. So each does one computation. Clearly, you end up in the same situation, right? It doesn't matter which one gets there first, right? Here, number 1 will first do its thing, and then number 2 does its thing. But you have actually just two processors, each doing one computation. Or like this, and they're not talking to each other. So clearly, the end, they will both have done a computation. That's it, right? It's essentially obvious, right?
Are they acting on the same shared local state?
No, each has its own local state. There is no shared state. No shared state here in this model whatsoever. Get rid of this notion of shared state. Shared state is evil, okay? No shared state. Each process has its own local state, which the others do not see. Okay? The only way that two processes can somehow connect is by sending messages. It's the only way. Okay? But it's clear, right? If I have two processors and they're sitting next to each other, each one of them does one computation, comp 1 and comp 2. One does it comp 1, 2 does comp 2. It doesn't matter in which order they do them, right? Because it will end up that both of them will have done their comp. So in C2, each process has done one computation step. Fine. But these two, it's just that they're done in different order. Who cares? They're separate. The intermediate states can be different, of course. The intermediate configurations. But at the end, each processor will have done one comp. Right? So you see, it's very simple, right? This is very simple, right? You understand it, huh? You have to understand this, huh? If you don't understand it, tell me you don't. I will not penalize you. I will penalize you if you don't understand it and you don't tell me you don't understand it. Then you will be penalized, but not by me, by the laws of exam correction, okay? Of which I am just an obedient servant, okay? So basically, if two processors run independently, it's clear that when both of them terminate their execution, it doesn't matter in which order, once they both terminate, the configurations will be the same, right? That's clear, huh? Right? Everyone is agreeing with me? Oh, now I'm disappointed. You all seem so perplexed. Okay, here's another case. Once you understand this one should be also understandable. Here I have two deliveries. Here I have a message jumping from 1 to 2. Here I have a message jumping from 2 to 3. So this is going from the out buff to the in buff, huh? This is going from the out buff to the in buffer, okay? So in del 1, 2, you have a message jumping from out buff 1 to in buff 2. And here you have a message jumping from out buff 2 to in buff 3. So, of course, it doesn't matter in which order you do them, right? If I first jump from 2 to 3, and then from 1 to 2, the final result is the same. The final result is that the two in buffs, 1 and 2, the two out buffs, sorry, will be empty, and the two in buffs, 2 and 3, will have the messages in them, right? So these two deliveries are also commutative. You see that? It's a very simple thing that I'm telling you here. It's basically, in a distributed system, you can have separate parts that are kind of doing their own thing, and because we have executions where we see the whole configuration, the C here in the configuration is all of the state of all the nodes. But that can be many nodes, and each part of the system can be doing its own thing, of course. So it's not because we're looking at the whole thing that it's not commutative. Yeah?
Just a question. When we do the delivery, in the first one, it sent the message M, and in the second one, it's M first.
I'm sorry, this should be M prime, and this should be M. Oh, very smart. You found a typo in my slide. Thank you. Yes, this should be M prime, of course, and this should be M. Thank you. Very good. You are completely right. That is a typo in the slide, and I will fix it. So here, the message goes into the in buff of 2, M goes there. So this should be M. Here, M prime goes into the in buff of 3, this should be M prime, of course. And then you see that it's commutative. These two events, and these two events, are called concurrent events. They're events such that the order does not make a difference. Okay? This is a part of the real world. If I'm reading a book, and my friend is reading a book, and I read page 1, and he reads page 1, those are concurrent events. Okay? It doesn't, when both of them are done, they have no effect on each other. They can be modeled in any order. Okay, you see that? Concurrent events. Okay, right? Well, now let's go to the next step. Here's another one. This is a case when the events cannot be switched. So here we have a green and a red one. This green one, I'm moving M from the out buff of 1 to the in buff of 2. And in this comp event, I'm doing a transition where I'm assuming there's an M in in buff 2. Okay? So clearly I cannot switch those, or the result, the state will be different. Okay? If I switch those two, the final configuration will not be the same, because M will not be in the in buff if I put comp 2 before. Okay, you see that? These two events cannot be switched. I mean, if you switch them, you will change the final configuration. So they have an effect. So they cannot be switched while keeping the same configuration. You see that? Because one of them depends on the other. You see it, huh? This one requires in S1 here, you need to have the M in the in buff, this transition here. Otherwise, you will not be doing the same computation. You see that? We say that these two events are causally related. There's a causal connection between them. So you see, in a distributed system, you can have either concurrent events or you can have causally related. Sometimes events are causally related, but we can actually define exactly when they're causally related. So this is one case when they're causally related, but we can define more precise. You see that there's a connection between these two. You cannot switch them without changing the result. Whereas in the previous case, you switch them, it affects nothing in the result here. These are concurrent. And the other one is, these two are causally related. There's a causal connection. Okay? We can actually define an order between events. A partial order, which is written like this. It's a less than with H. It's pronounced happens before. If A occurs before B on the same process, then A happens before B. Because, of course, the A will create a state, which is the input state for B. So if you switch them, the result changes, okay? So we see that these two events are causally related. A happens before B. But you can also see with the delivery, if A does a comp, which creates a message M, and B delivers M, so basically A creates M in the outbuff, and B actually sends M to another machine, then these are also related. Because if you switch them, the result is different. So in this case, A is like doing local, is like doing a send, and B is like the receive, right? Where the message appears on the other node. Then A is happening before B. Okay? And in the opposite case, if A delivers M, so the M arrives, and B is a computation that uses M, then again A happens before B. Okay? And then there's the fourth rule, which is the really interesting one. This is a transitive order. If A happens before B, and B happens before C, then A happens before C. Because if you switch any of these, the result is different. So there's a causal connection here and here. So C depends on B, but since B depends on A, C will also depend on A. Okay? If you don't have the A here, you won't have the B, so you won't have the C. So this is transitive. Okay? So this relationship is the key thing for a distributed system. Causal order is the most important concept for a distributed system. Okay? So this is something you have to understand. And we're going to talk a lot about causality. And when you're actually building real distributed systems, it's super important, as we see. Okay? So this happens before. And we also say two events are concurrent if it's not the case that A happens before B, and also it's not the case that B happens before A. So A and B don't depend on each other, and we write it like this, with two vertical bars. A and B are concurrent. Okay? See that? So that's really important. So here we have these two events. This one happens before this one, and here we have two examples of concurrent events. What happens before is transitive. This is the big thing. That means it's all over the place, okay? So here's kind of like an example. Here I introduce kind of a visual notation. This is called a time-space diagram. It's nothing to do with relativity. So Einstein has nothing to do with this. Although you can generalize distributed systems for relativistic effects, but I will not do that in this course, because we're looking at systems running on planet Earth, okay? So usually the causality does not depend on that. So this is called a time-space diagram, because we have each process here, and time is running from left to right, and we mark all the events on the process. So this little loop here is a comp event. This is a comp event. Then we have an arrow running from one process to the other. The beginning of the arrow is actually a comp event that puts something in the out buff. So here you're putting in the out buff, and this transition is moving the out buff to the in buff. So at the head of the arrow, the message appears on the in buff. So the del event is happening here, okay? And here we have a comp event which puts something in the out buff. So that's a reasonable way of looking at it. So you can also say putting in the out buff is like, you can call it a send. And when it appears in the in buff, you can call that a receive, okay? And there's this instantaneous transition here. But the putting in the out buff and the del are not happening at the same time. So these vertical bars are the instance in the execution. These instances, 1, 2, 3, 4. So we can order the events, huh? So this is the first event, the second, the third, the fourth, fifth, sixth, seventh, and eighth events. Okay? We can order them in our execution. Now you can see that there's causal, you can see the causal connections here. These two events, P1 and P2, are concurrent. Because if you switch them, it changes nothing. You do a computation at P1 and one at P2. It's the two comp events. Okay? These two events are causally related. Okay? Because here we're doing a comp event and here we're doing another comp event on the same process. Okay? Here, these two are causally related. We're putting in the out buff, taking, and then transferring to the in buff. And the same here. But these two events at the edge of this path here are also causally related, because we can only do this if there's the message here. But this message here depends on this. And this one depends on this. And it's also depending on this. So this event and this event here are causally related. This is the transitivity rule, huh? Because there's this transitive connection between these two and these two. Okay? And so these two, these two, these two, and these two. So there's a bunch of events here. 1, 2, 3, 4, 5. Huh? Okay? See that? So causality. So this is something we're going to make a lot in this course. I'm going to make lots of these diagrams, and we're going to be seeing lots of things happening. Okay? Okay. So this is causality. But now I want to take a step back. This time-space diagram is like a God's eye view of the system. I see the whole system when I look at this. At any instant, I can see what happens everywhere. Now, the real world is not really like that. When I'm sitting on a machine, I can only see what happens on my machine. So in the real world, I can only see the horizontal line, okay? This whole view of the system is not something that is usually available to the algorithm. It's something that you can reason about, you can think about all that, but you can't actually see it inside the algorithm. What you can see is just a single process. What you can see is called the view of PI. So if I'm sitting on a process, that's PI, and I'm looking at what's happening here, I can see the messages coming in, I can see the local computations, and I can see the messages going out. That's all I can see. I don't know anything else. That is the view. So this is E restricted to PI. So E is like the God's eye view. The whole execution of the whole system. And if there's 1,000 nodes, it's a big thing. But no single processor can see that. Because in order to see that, you have to instantaneously see what's going on inside all those processors. And you can't do that because they're connected by network. They're far away. Okay? All you can see is the view of a PI. So then you can see if two executions, E and F, different executions, but in PI they look exactly the same. So if I'm sitting in PI, I'm receiving the same messages, sending the same messages in the same order, same computations. The two executions are similar with respect to PI. Okay? Fine. But they might be very different. It's just on PI they look the same. But now I can look at this. What if the two executions are similar with respect to every single node? That means every single computer sees the same sequence of things. What does that mean? Are they actually doing the same thing then, or not? What does that mean? If two executions are similar, if they look the same on every node, but is that the same as them being the same everywhere, or not? You see, that's an interesting question, huh? we can actually say something about that. Okay? So here's a theorem. So here, this is an important theorem about causality. So let's say E is some execution, okay? C0, E1, C2, C1, E2, etc. And there's a schedule in here, E1, E2, E3. Okay? This is some execution. Now, let's take a look at this schedule. Let P be another schedule, which is a permutation of V. So I'm moving things around. So P is another schedule, F1, F2, F3, but it's the same events here, which is just in some different order. Okay? But there's a condition here. It preserves the causal order. So for example, if Fi happens before Fj, this implies that I is less than j. Okay? I'm not reversing causality. Yeah? So this has some causal order. And in V, if Ei happens before Ej, Ei has to be before Ej. I cannot travel backwards in time. If you look at the definition of causal order, you will see that happens before is only possible if the event is really before the other one. You cannot travel backwards in time. So V, of course, is respecting that. Okay? But assume that P also respects that. That P, if Fi happens before Fj, then Fi will also be before Fj. So I'm not breaking causality. Well, in that case, E will be similar to the execution using P. That means if you move around the events, but if you preserve the causal order, so you don't travel backwards in time, you keep traveling forward. So basically what you're doing is the delay, the dells can be delayed, but only towards the future, okay, not towards the past. No? The dells can be delayed, basically, in P. Because you're respecting causal order, they will only be delayed towards the future, not towards the past. Okay? If you do that, if you respect causal order, then E will be similar to the execution of P. So that's actually interesting, okay? That's actually very important. It's actually not so easy, not so hard to prove that. So I'm not going to prove it right away. Maybe some will see it later. But now I want to give you more the consequence of this. Okay? If two executions have the same set of events and their causal order is preserved, so they're doing the same events, but in some different order, but the causality is preserved, so I'm not traveling backwards in time, then they're called similar executions. It's written like this. F is similar to E. Similar executions. Okay? But actually, they're doing the same work. If that is the case, they will end up, because they're respecting causality, they will end up with the same results. Okay? So now we have something interesting. We have a whole bunch of executions that are different, but causally they're the same. Okay? Causally they're the same. This is actually an equivalence class. All similar executions are an equivalence class, and this class is called a computation. So equivalence class is a mathematical concept. It means that if I have two executions that are similar, it's reflexive, so an execution is similar to itself. Okay, that's obvious. The permutation is doing nothing. Okay, it's symmetric. If A is similar to B, B is similar to A. Okay, and it's transitive. If A is similar to B, B is similar to C, then A is similar to C. And this is called a computation. It means then I'm allowed to shuffle around the events. As long as I respect causality, I'm doing the same work. I'm doing the same thing. So here's some examples. So it's important to kind of get the intuition of this, huh? So here I have 3 executions. So the executions, so these are events, huh? All these are events. But they're somehow in a different order. But these 3 executions are actually similar to each other. And you can see that because if you look at each process, you see the same things. So if I look at P3, I see this one, and then I see this one. If I look at P3 here, I see this and this in the same order. If I look at P1, I see tongue like that, but also always in the same order. The timing might be different, but it's from each process, it's the same order. So the 3, and it's true for all 3 here, for all these 3 executions, so they are doing the same computation. Causality is preserved. So for example, the pink ones here, this pink chain are causally related events. Tongue. Here the chain is also the same. Tongue, in the same order. Here also the chain, sometimes it's stretched out, sometimes it's compressed, but the order is the same. So the causality is preserved. So they're actually doing the same thing. They're doing the same computation. The result will be the same, okay? Because they respect causality. So that means that each time you do an event, you are basing it on the same previous thing, so you're doing exactly the same work. You see that? So executions are not really the thing, because you can have lots of variations on the executions. The thing that really determines what you're doing is the computation. This is somehow you factor out the causality, okay? So there's a couple of results of this. So this maybe would give you some intuition. This theorem implies 2 results. First of all, no algorithm can see the time-space diagram. That means if I run a distributed algorithm, okay, I run an algorithm, and at the end, I ask the algorithm to make a printout of this diagram. So in this case, it would print this. In this case, it would print this. Or here it would print this diagram. That's impossible. No algorithm can see it. Because from the viewpoint of the algorithm, these 3 things are exactly the same. Okay? So an algorithm, no algorithm that's running inside this model can observe the order, the actual global order of the events. It can only see the causal connections. So and there's no algorithm that can see or print out, if you want that, the time-space diagram. It doesn't work. It doesn't exist. Okay? Huh? And you can easy to prove. Assume you have the algorithm. Assume node P knows this. But if I have 2 similar executions that preserve causality, according to the computation theorem, they have to have the same final configurations. And the configuration is the state of all the nodes. So nothing is different. So you cannot see the different time-space diagrams. Okay? And another result, you can extend the model and do more, of course. If you add hardware clock, if you add an actual hardware clock that is counting the nanoseconds or something on the machine there, to each process, if you add a hardware clock, then the theorem does not hold anymore. Then you can see things. You can see hardware clock is an important thing, huh? So normally you don't want your algorithm to depend on hardware clock. But if you have a hardware clock, each process can read the local clock whenever there's an event, and the final configuration will have different clock times because the executions, the events are happening different time, okay? So that's not possible according to the computation theorem. That means the hardware clock breaks things. With the hardware clock, you can make the difference, okay? See, but if you don't have a hardware clock, causality is the only thing you can see is causality. You have causality glasses on. When you're running a distributed system by default, that's the only thing you see. Huh? You can say causality is all that matters. Okay? So that's an interesting result, okay? If you want to go away from that, you have to do extra things. But by default, causality is all that matters. Okay, so causality, you can detect it. You can, it makes a difference. If the causality is different, things will change. If the causality is the same, things are the same. We can actually define causal clocks that respect the causality, and they're called the Lamport clock and the vector clock. And these clocks are actually going to tell us what is the causality. Yeah? These clocks will tell us basically what are the causal connections. If I look at these two events, the clock will tell me that this event is causally before this one, for example. So that I can do. As long as I'm inside of causality, I can do it. Okay? And there's two famous clocks that you can compute. This is Lamport clock and vector clock. So I present it. So the Lamport clock is the easiest one. This is actually, it's called a logical clock, as opposed to physical clock. A physical clock is a device that counts time, wall clock, nanosecond. But a logical clock only clocks the causality. It's like an abstract clock. Okay. And the Lamport clock is a logical clock, and it's very easy. Each process keeps a special variable, t, t for time, which starts out being 0. And each time you send a message, you piggyback, you add t to the message. So when I send a message between one process and another, the other one will find out what is the t value. Okay? So there's some connection between them. And when I have an event, I have to update t. When I do a comp event, I just increment. So one more event. Okay? But when I receive an event, I take the maximum of the one on the message and my local one, and I do +1. So the t somehow tells me what is the maximum number of events that are causally before me somehow. Huh? Okay? Okay, let me show an example of a Lamport clock. So here we have some kind of time space with things running, and the three clock values are 0 here. So the first one I do now is an event here. So what will be the values of the clocks after this? You tell me. What's going to happen now? I'm calculating Lamport clock. Here. I do one step. So right after this event, what is the value of the clock here?
1.
1. And what is the value here? 0. Stays 0. So it's 1, 0, 0. Okay? So that one turns into 1. And the next one, of course, will also make it 2. Okay? These are still 0. So here, I'm doing a comp event that puts something in the out buff. So it's a send. So the Lamport clock will be incremented. 3. And now the next event is this one. Okay? So that one will be from 0 to 1. Okay, and here, what do I get? I have now the piggybacked message, and I also have this one.
It's 1.
So it has to be more, right? It has to always increase. It's going to be the max plus 1. It never goes down, it always goes up. Okay? It's going to be 4. Because I have a 3 here and a 0 here. This is piggybacked. So I receive the 3, and I also know 0. So I take the max of those 2 plus 1. So that gives me an upper clock. What does it tell me? It tells me that there are events, there are 4 events. There's a path of 4 events that are causally behind me. That's what's telling me, this 4. 1, 2, 3, 4. That are behind me. Okay, and here, what happens when I do this one? 4, so what? Yeah. And here now, 5, right? Yeah, because it's one more event here. And then the next one here will be what? 6. So you see, it's not hard to calculate this, but you have to know what it means. So what does this number mean, actually? Well, it's telling me something about causality. For example, these 2 events, 1 is less than 2, 0 is less than 1. So it's telling me something about the order of the events, right? So in fact, if you look at the guarantee, so this is what a Lamport clock guarantees for me. If A happens before B, then the Lamport clock of A will be less. So this is an integer, positive integer, will be less than the Lamport clock of B. Okay? So if I know that A and B are causally related, then it will tell me which is first, which is that happened before one. Okay, let me skip this for now, I'll talk about it later. But it's not telling me everything, Some things it's not telling me, For example, these 2 events, for example. These 2 events, what is the connection between them? What is the causal connection between this one and this one? Are they concurrent? Is one of them happening before the other? So the Lamport clock is 1 and 4, But this one happens before that one, Because I can put it here, and it will not change anything in the execution, So the Lamport clock does not tell me everything, It actually only tells me a little bit. There's a lot of things it doesn't say. So if 2 events are concurrent, the Lamport clock is meaningless, bogus. It doesn't tell me anything. It only tells me something if the events have a causal connection, like on this chain here. Between these 2 events are causally related, and this one is before this one, and 2 is less than 5. It tells me which one is first. But between these 2 events, which one is the first one? They're concurrent, so there's no one which is the first one. But the Lamport clock will not tell me 1 is less than 4, but that's not saying anything important here. You see? So the Lamport clock, it only gives me half of the story. You see that? The Lamport clock only goes in one direction. If they're causally connected, then the Lamport clock is less. But it doesn't go the other way. What if I want to know whether or not they're causally connected? The Lamport clock is not telling me that. Okay? Despite the fact that Lamport being a very famous guy, the Lamport clock is a very weak thing. Okay? But there's another kind of clock which does tell me everything about causality. It completely specifies causality. It tells me everything. This is one is called the vector clock. So this is actually the best one, if you want, but it's more expensive than the Lamport clock. The Lamport clock has the advantage it's very cheap. It's only 1 number per node. But the vector clock, each process has a vector, so an array of size n. N is the total number of processes. Okay? And initially, the vector is all zeros. So each process stores a vector. So this is not really scalable. Huh? If I have 1,000 nodes, then each process has a vector of a size 1,000. Okay? And the way to update the vector is when I do a comp event, I will increment only one of the components, the P component. And when I also have to piggyback. And when I receive a message, I do the maximum for each element. So the vector is telling me something about all the nodes. It's not just one number, huh? Okay? So the vector clock will tell me if the events are concurrent, which the LINFO clock did not do. Okay? So if here I have two vectors, and I can compare the vector clocks. So if the vectors are less than or equal for all items, then the two vectors are less than or equal. If they're different, then it's strictly less than. And if they're not less than, VP is not less than Q, and Q is not less than P, then the vectors are concurrent. So it will tell me concurrency. So the vector clock tells me both directions. If A happens before B, then the vector clock is less. But if the vector clock is less, then I know that A happens before B. So the Lamport clock did not tell me that. Okay, so I have to show you an example of this. So here's a vector clock. You see that I have three vectors here, 0, 0, 0. And I do one event here. So what is the vector now when I do one step? It's what here?
1, 0, 0.
It'll be 1, 0, 0, because I'm only updating the component where I'm at. So it's 1, 0, 0, oops, and this one is 2, 0, 0, okay. And the next one will be
3, 0, 0.
3, 0, 0, okay. And now this one is what?
And this one is 0, 1, 0.
0,
Oh, 0, 0, 1.
0, 0, 1, because I'm on P3. Okay. And here now, I have piggyback.
3, 0, no, 3, yeah, 3, 1, 0.
3, 1, 0. So the max, but I also have to increment that. So it's 3, 1, 0. And here, what do I have?
4, 1. No, 4, 0, 0.
4, 0, 0. See that? 3, 0, 0. I increment the first one. And here I have
3, 2, 0.
3, 2, 0. Right? And here I have what?
3, 2,
3, 2, 2.
Well, I have 3, 2, 1, but I have to do a little bit more. 3, 2, 2. Okay. So what is it? What is this clock telling me? It's telling me something, huh? The intuition is that each of these vector is telling me, this one, for example, is telling me what does P2 know about all processes. So P2 knows something about P1, it knows something about P2, and it knows something about P3. P2 knows that there are 3 events causally before this one on P1. That's the 3. It knows there is one event, which is this one, because this is the clock after, before this, at this position, and it knows nothing about P3. So it knows there are 0 events causally before this one on P3. Okay, so 3, 2, 2 is telling me what does P3 know. Okay, so P3 knows something about P1, about P2, and about P3. It knows there are 3 events causally before this one. It knows about 3. Of course, there's another one here, but it's not causally before this one. But these 3 are causally before this one. It knows there are 2 events causally before this one on P2, and it knows there are 2 events on P3 that are causally before. This is the thing just after. So it's basically telling me what does PI know about everybody else? So I have knowledge about everybody, and it's telling me how many causal events are before me on all the other processes. That's what it's telling me, okay? That's what it's telling me. So that's very good, but the bad thing is that you can't compress these vector plots. You can't make them smaller. So people have tried, researchers have tried to make them smaller, but you can't really do it. If you have n nodes and you want really to know causality, you need vectors of size n. That's it. Okay. Okay, I'm a little bit over time, so I stop here. So you've now learned about causality, okay?